Hello everyone, and welcome to this video about stationary points. So just to recap from before, a stationary point is where the gradient is equal to 0. And in order to find the exact x value at where this turning point or stationary point will happen, we will simply equate the derivative to 0, and we will then solve it in order to find the x value at which the maximum or minimum point will occur. So this is obviously going to be a maximum point, and this is going to be a minimum point. And later on in this video, we are going to link this to the prior section on second order derivatives, and that's going to help us to determine the nature of the stationary point, which means is it a maximum, is it a minimum point? Okay, so let's go ahead and look at our first example. Find the coordinates of the turning point of y equals x cubed plus 6x squared minus 135x. So first of all, I'm just going to find my gradient function. So I'm going to differentiate, and I will get 3x squared plus 12x minus 135. Now, before I continue, I must add that you should feel free to pause the video and have a go at this yourself, and then play it again and see if your answer matches up with what I have done. Okay, so let's continue. We know that the stationary point, which I'm just going to label as SP, is when dy by dx is equal to 0, which means we are going to set this gradient function equal to 0. I'm going to simplify this before I solve it. I'm going to divide by 3 throughout this equation, and I will get x squared plus 4x subtract 45 equals 0. And then we factorize, and we will get x plus 9, x subtract 5 equal to 0, which gives me x equal to negative 9 or x equal to 5. And this simply means that if I were to sketch this cubic here, I know that when x is negative 9, so let's say that's all the way down here, I'll have a turning point, and when x is equal to 5, I will also have a turning point. Then if I wanted to go a little bit further or just look for connections here, I can see that I've got plus 0 there. There's no constant. So I know also that it's going to go through the origin, through the axis, or on the axis. I still need to find my corresponding y value. So I'm going to sub in x equal to 9 here into y, sub into y, my original equation, y equals x cubed plus 6x squared minus 135x, and x equal to negative 9 into this equation. Use your calculator to do that. Be very careful. You want to be putting brackets around the negative numbers, because if I have an odd power, it will stay as negative. The same here, you want to make sure your calculator solves this correctly. 6 times negative 9 squared, subtract 135, take 9, and that's going to give me 972. So I know that at the point when x is minus 9 and y is 972, so minus 9 and 972, I will have a stationary point, a turning point. I do the same for when x is equal to 5. When x is equal to 5, I'm going to sub that all in. I get y equals 5 cubed plus 6 times 5 squared minus 135 times 5, and that gives me negative 400. So I then know at 5 and negative 400, I will have a turning point. goes through 0, 0. So I'm going to end up with a cubic that is not drawn to scale, obviously, but looks a little something like that. So I've got one maximum point and I've got one minimum point. Okay, right, let's look at another example. Find the least value of which f of x is equal to x squared minus 4x plus 9. Well, let me rephrase that. Find the least value of that quadratic. And that literally means the least value means the lowest point. What is the lowest y value for this graph? So if I had to sketch this graph, what is this value? This is the least value. So first I'm going to have to find the x value at the turning point, and then I'll have to sub it in order to find the corresponding y value. That's what a question like this is asking you to do. There are two ways you can do this. You can either differentiate, use the same method as we've done before, and we'll do that first, or because it's a quadratic and this only works for a quadratic, I can also complete the square, because I know when I complete the square, minus a comma b gives me the turning point, and that will be my least value. That's my y value, and that will be the x value at which the least value occurs. But let's just first stick to the method we did before, method 1, and we are going to differentiate. Okay, I'm going to find the gradient function, which is 2x minus 4. I know that when the gradient function is equal to 0, I have a turning point, a stationary point, or a vertex. So I'm going to let this equal 0. So 2x is equal to 4, and therefore x is equal to 2, which makes sense. When x is equal to 2, I have a turning point. So I'm then going to find y, and I say I have to go back to the original equation, so I'm subbing 2 back into f of x, which gives me 2 squared minus 4 times 2 plus 9, and that is 4 minus 4, so that is 5. So I know actually that the sketch which I guessed this to be is incorrect, because it has to be at y equal to 5, and this is obviously a negative y value. So it's actually going to look something like this, where that's 2 and that's 5, 2,5. Okay, so method 2, hang on, before I move on, this here is then my least value of f of x, or also known as the minimum value, the lowest y value, the lowest value that curve dips down to. Okay, so method 2, because it is a quadratic, I can complete the square. So let's do that. X squared minus 4x plus 9 gives me x minus 2 in brackets. Subtract 2 squared plus 9. That becomes x minus 2 squared plus 5. So my stationary point is at 2,5, and so my minimum value, or the least value of f of x, is 5. Okay. Now, let's move on to the next section, which is looking at determining the nature of a stationary point. So let's just talk a little bit about this. Made a little diagram here. It's probably not the best diagram ever. Let me redraw this and be a bit more specific, a bit more clear. Okay, here we go. That looks better. There's a turning point. There's a turning point. And there's something that can be confused or mistaken for a turning point. But let's first look at this point here. This is a maximum point, right? And I know it's a maximum point because the gradient actually changes from positive to, well, it's 0 there at the maximum point to negative. So for a maximum point, the gradient before, it goes from positive to 0 to negative. Okay, so that's how you can determine whether something is a maximum point. Here I have a minimum point. And a minimum point is where my gradient goes from negative to 0 at the exact turning point to positive directly after the turning point. And that gives me a minimum point, sometimes referred to as a local minimum and a local maximum. And then lastly, I have this point here. And as you might notice here, that prior to this point, the gradient is positive, and after, the gradient is still positive. And when this happens, when the gradient just before and the gradient just after does not change sign, it means I have a point of inflection. Okay, and to determine a point of inflection, we will have to look at the gradient before and the gradient after and see whether it changes sign or not. If it doesn't, then it could be that we have this point of inflection. But we are actually for this video just going to focus on finding maximum and minimum points without having to sketch the points, without having to sketch the graphs. Okay, so question 1, find the stationary point on this curve and determine whether it's a local maximum, a local minimum, or a point of inflection. Okay, so we need to find dy by dx first, and we will do this, dy by dx. Pause the video, have a go, and then play it again and have a look and see if your answer compares to mine. Okay, so dy by dx will give me 4x cubed minus 32. I know that my stationary point, SP, is when dy by dx is equal to 0. So therefore, 4x cubed minus 32, I set equal to 0. I'm going to solve this. So I end up with x cubed equaling to 8. And the cube root of 8 is 2. Okay, so I can set up a table now that looks a little bit like this. This is one method. I should call this method 1. Right? Method 1 is gradient. Look at the gradient. Look at gradient before and after the stationary point. So I know when x is equal to 2, the gradient is 0. This is my gradient. Okay. So I pick a value just before. So let's say 1.9 or 1.99. And I pick a value just after, let's say 2.1 or 2.01. It does matter, but the examples we look at will just assume that 1.9, 2.1 before and after won't change. So when I calculate the gradient for 1.9, I'm going to sub x equal 1.9 into dy by dx. Okay, so 4 times 1.9 to the power of 3 minus 32, and I get an answer of negative 4.56. So the gradient is negative, which means the shape is going to look like this. The shape here is horizontal, and when I sub in sub x equal 2 into dy by dx, well, then I'm going to get 4 times 2 cubed minus 32, and that, sorry, it's not 2, it's 2.1. 4 times 2.1 cubed minus 32. That will give me 5.04, which is positive 5.04, and the shape looks like this. So that means I have a minimum point. Around 2. So I found that for x equal 2 I have a stationary point. I've just determined it's a minimum point. If I had to find the entire point, I still need to find the y value. So y is equal to 2 to the power of 4 minus 32 times 2, and that gives me negative 48. So the turning point will be at 2, negative 48. And we have already determined that that is a minimum point. Okay. Method 2 is using the second derivative. So in the previous video we looked at finding the second derivative, and the second derivative is really useful in determining the nature of the stationary point, because the first derivative is the rate of change. It's how y changes with respect to x, and the second derivative is the rate of change of the gradient. Gives us the rate of change of the gradient, which means if I were just to sketch this and show this to you, right? If I have a maximum point, I know that on this side I will have a positive gradient. I will have a gradient of 0, and on this side I will have a negative gradient. So if I differentiate the gradient function, the second derivative, so d2y by dx squared, tells me the rate at which the gradient is changing. So if the second derivative is positive, that means the gradient is increasing, right? If the second derivative is negative, then the gradient is decreasing. Okay? And at a maximum point, such as in the example here, at a maximum point, as x increases, and with that I mean, remember, x is on this axis, y is on that axis. As x gets bigger and bigger, as x increases, the gradient is decreasing, right? It's decreasing, it's positive, 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 but then it goes 0 and then it goes negative. So for a minimum value, the d2y by dx squared will be greater than 0. But for a maximum value, such as in this example here, for a maximum turning point, we see that the gradient is decreasing from positive to 0 to negative, right? So for a maximum point, d2y by dx squared will be negative. And for a minimum point, d2y by dx squared will be positive. And I'm going to show you that now using this second example again. We found dy by dx already. It was 4x cubed minus 32. We're now going to find the second order derivative. That's going to give us 12x squared. Well, minus 32 becomes 0. So remember how we found the turning point, the vertex, to be at x equal to 2. We've already shown that this is a minimum point. We already proved it using the method 1, looking at the gradient before and after the stationary point. But now look what happens to the second order derivative. When x is equal to 2, d2y by dx squared is equal to 12 times 2 squared, which is 48. 48 is positive, it's greater than 0. And this corresponds with what I said here. If it's positive, it must be a minimum point. Therefore, it's a minimum point. We've proven it. We looked at it here. We know it must be a minimum point. I then showed you this bit of theory, showing that the gradient decreases from positive to 0 to negative, which means if the gradient, the second derivative, is negative, then the gradient is decreasing, which means I have a minimum point. Sorry, a maximum point. Okay, so in my opinion, just using the second order derivative is simpler, it's quicker. However, it could be that we have a point of inflection. So when my second order derivative is 0, it could imply that I have a point of inflection, and I will then have to test. I'll then have to use this table method. Okay, right. So let's move on to an exam question. We are given this curve C, y equals 4x cubed minus 9x plus k over x. They tell us the point P with x coordinate a half lies on C. They also tell us that P is the stationary point of C, and we need to show that k is equal to negative 3 over 2. So stationary point, when you see that, you know that dy by dx is equal to 0 at that point. And we already solved it, or they've already given us the answer to that. They told us that at that point x is equal to a half. And we're going to use this information to work out k. So let's get going. Part A. I've got y equals 4x cubed minus 9x plus kx to the minus 1. I first need to rewrite this before I differentiate. Okay, dy by dx, that is 12x squared minus 9 minus k x to the minus 2. Okay, so this is my stationary point when I make it equal to 0. Okay, so 12x squared minus 9 minus k, and I'm just rewriting this as x squared, equal to 0 is where my stationary point is. They told me in the question the point P with x coordinate a half lies on C, and P is a stationary point. Therefore, x equals a half is a solution to this equation. So I can go and sub in x equals to a half. And I will get 12 times a half squared minus 9 minus k divided by a half squared equals 0. Okay. That gives me 12 times a quarter, 1/4, minus 9 minus k divided by 1/4 equals 0. So 12 times 1/4 is 3. 3 minus 9 is minus 6. And I'm just going to move that to the other side, so I get k divided by a quarter. And so therefore k is equal to minus 6 times by 1/4. And so k is equal to negative 6 over 4, which is negative 3 over 2. So I've worked out the constant in this equation. K is negative 3 over 2. So even if you couldn't do this bit, you could assume it's true when you go on to the next part. In the next part they say determine the nature of the stationary point at P, justifying your answer. So we are going to use d2y over dx squared. And we're going to see, is it positive or is it negative? Because if it's positive, it's a minimum point. If it's negative, it's a maximum point. Okay, so we know that we have here dy by dx, and we now have a k value. So I'm going to write dy by dx with my k value subbed in. Minus negative 3 over 2 x to the minus 2. I'm just going to simplify this. 12x squared minus 9, and that becomes plus 3 over 2x to the minus 2. Now I want to get this right because I want to find d2y by dx squared. So I differentiate and I get 24x minus 9 becomes 0, and this becomes minus 2 times 3 over 2. Well, that's going to cancel, so I'm just left with minus 3. So minus 3x to the minus 3. And I can rewrite this as 24x minus 3 over x cubed. Right, remember I want to determine the nature of the stationary point. So I need to sub in x equal to a half, because I know at x equal to a half, that is where my stationary point lies. P is a stationary point with x coordinate a half. So when I sub that in, d2y by dx squared is equal to 24 times a half minus 3 divided by 1/2 cubed, which gives me 12 minus 3 divided by 1/8. And dividing by an eighth is timesing by 8. I mean, you by all means use your calculator. I'm just doing this non-calculator here, so which is why I am simplifying things in this way. So d2y over dx squared is equal to negative 12. This is less than 0, therefore it's the other way around. It's a maximum point. This is my justification, this bit, by saying it's less than 0 and therefore a maximum point. I have just gone and proved that. Okay, so that covers everything I wanted to go over the nature of stationary points and using the second order derivative. We will practice this some more in class. I hope it's been useful. As always, if you have any questions, please do let me know.